So today we're going to talk about graphing functions using translations and transformations. And the premise of today is we're going to be working with these things called parent functions. All right. Now, parent functions are basically like stripped down versions of cars, no air conditioning, no electric windows, et cetera, et cetera. They're basic functions. And what we're going to do is we're going to take a look at the graphs of those basic functions, look at the general patterns that they make, and then we're going to move them left and right, up and down. We're going to expand them. We're going to squeeze them, and just change the general look based on some certain functions. All right, so let's start with x squared. We know from freshman year it's quadratic. If we didn't know how to graph this, probably be good to pick points. I'm just going to go 2, 1, 0, -1, -2 is my basic pattern for this. Plugging it into x squared, I get 4, 1, 0, 1, 2, right? And if I graph it like so, I'm going to get a parabola. And anything with that x squared form is going to be parabolic in nature. Curved, not like an absolute value, etc., etc. Now, x cubed, you may not have graphed too much, but it's going to have a basic pattern too, and I'm going to use small numbers. So we call our x and our y, and we'll go 2, 1, 0, -1, 2, just to keep things small. And I get 8, 1, 0, -1, -8. I go ahead and graph that. There's my 0, 0, my 1, 1, 2, 3, 4, 7, 8-ish. There's 1, and then 2, 3, 4, 5, 6, 7, 8-ish. All right, and this graph looks very similar to this. All right, it rises a lot quicker. All right, let's look at a couple more parent functions. We'll look at the absolute value of x. This guy again, picking x's and y's. We'll go -2, -1, 0, 1, 2. And I get 2, 1, 0, 1, 2. Graphing, once again, you'll notice in this case, it has a similar shape to a parabola, except it forms a straight line on each side. So it's like a V, if you will, or a check mark, I don't know. Square root of x, well, if I want to pick nice numbers to graph, I better pick perfect squares. So let's pick some perfect squares for x and y. And we'll get 0, 1, 4. If I want 9, I could get 0, 1, 2, and 3 out. So 0, 0, 1, 1, 4, 2, and roughly 9, 3. Somewhere like this. This is almost a one-way type of graph that curves. All right. And let's do one more. Cube root of x. So we have to pick perfect cubes in this case in order to get some nice values to graph. So we'll go 8, 1, 0, -1, -8. Then I get 2, 1, 0, -1, -2. Graphing that, there's 1, and then 2, 3, 4, 5, 6, 7, 8. Roughly here, there's -1, 2, 3, 4, 5, and roughly 8. So we're coming around, swinging down like this, like such. Okay, so these are all the parent functions that I'm going to hold you responsible up to this point. All right, now, turns out that all graphs can be written in a specific way using a specific generalized formula. And here it is. All functions can be expressed in this form where y is equal to some a times f of x minus h over b plus k. Now, what I want you to notice right here is this f, okay? This f corresponds to the function, all right, and the function's value. So if it's a square root, the function is a square root function. If it's a squared, it's the squared function, et cetera, et cetera, et cetera. And what we're going to do is we're going to take and isolate each one of these unknown variables and see what kind of effect it has on our problem. Let's do remember, though, that x is an input and y is an output value. Everything else is going to have some effect on my basic function. So here we go. We're going to look at our first graph of y equals x squared. And we know y equals x squared looks something like this. There's our parabola. Now what I'm going to do is I'm going to pop this into my calculator, and you might want to do the same. I'm going to go to y equals, plug in my x squared, and then right below it I'm going to plug in y equals the quantity of x minus 2 squared. So let's do that. So here we are with our calculator. We've got y equals x squared and y equals x minus 2 squared. I'm going to take and graph that. And you'll notice when I do so, there's x squared, and here's x minus 2 quantity squared. Now you'll notice this appears to have slid over. And the only way we could tell that it was the same exact shape that slid over is look at the pattern. So I'm going to look at my table values. I'm going to go second table. And you'll notice that my first function, y sub 1, is our y equals x squared, 0, 0, 1, 1, 2, 4, et cetera, et cetera. But you'll notice the other graph, all right, has the same pattern. Here's 0, 1, 4, 0, 1, 4. So that's up 1, up 4, et cetera, et cetera, et cetera. And look at where the vertex of the graph was. It was at 2. And then if I move 1 over to 3, then I go up 1. If I move 2 over to 4, I go up 4. So really, this is the same graph. It's just slid. So what I've done now is I've gone over 2, and then my pattern's still the same. And the pattern that I'm talking about, once again, is the pattern of our parent function of 0, 0, 1, 1, 2, 4. Now, if I were to take and graph y equals x plus 5 in my calculator, what you'll notice is 1, 2, 3, 4, 5. My vertex actually moves to the left, but my pattern remains the same. From this vertex, I go over 2 and up 4, and I get to another point, except I just went over 3, so I'm going to go over to 4. And there's our parabola once again. And they're all the same parabolas, they're just translated to the left and the right. So what we can learn from this is that, first of all, when we look at our general formula, this functioned like the h value in that general formula. And you'll notice that in the general formula, I have y equals a f of x minus h over b plus k. We've been messing with the h value. And you also notice that the h value follows a minus sign. So h is a horizontal translation, and it moves all points either to the left or the right. Let's go back to our examples again. So in this case, h was after the subtraction sign, and it was 2. So it moved 2 to the right. In this case, it followed an addition sign. If I were to rewrite this, this would be x minus a minus 5. So h in this case was equal to negative 5, and it moved everything back 5. All right, now let's take a look at another function. We're going to look at the absolute value of x, and we've done that before. Here's my pattern. And if I were to take and plug this next guy into my calculator, what I'd end up with is the following. I'd end up with this graph here. And you'll notice the graph in blue has been moved up 5, which makes some sense because we're taking whatever the original y values were and adding 5 to them. So again, in this case, we're messing with our k values, and in this case, k was 5. In this case, k is equal to -2. So you might be able to guess that if I were to graph y equals the absolute value of x minus 2, that all the points would move down 2. And so my new graph would look something like this. But you'll notice each of these graphs, if I slid them on top of each other, they perfectly match because they have a pattern of 0, 0, 1, 1, 2, 2. On both sides, I can even go -1, 1, and -2, 2. And once again, let's take a look at that general function. I know that if I have h following a subtraction sign, it moves left and right. And if I have k always following an addition sign, positive k moves everything up, negative k moves everything down. And let's move to our next example. So now you'll notice in this case what we've done is we have this term in our denominator. Actually, let's go, let's go to this example first. Skip forward a little too much. All right. So what I want to do now is I want to take and I want to graph this square root function. Now I know typically the pattern of my square root function, if I were to plug in just the square root of x, would be 0, 0, 1, 1, 4, 2. But in this case, I have an h and a k value. My h value is always inside the function, and the function here is a square root, and it follows a subtraction sign. So in this case, h is equal to 1, which means everything is going to move to the right 1. The k value follows an addition sign outside the function, and that in this case is 5, so everything's going up and down. So what I do is I think of, well, rather than moving every point, I'm just going to move my starting point or my origin point. So my origin is going to move 1 to the right and 5 up. And what I do there is I put in this fictitious little origin and set of axes. So now what I'm going to do is I know that if I only have h and k added to my problem, from my previous examples, I know the only function they have is moving the graph. Otherwise, the graph looks exactly the same. In other words, it has the same pattern. So from this new origin point, I'm going to graph my square root pattern of 0, 0, over 1 and up 1, and over 4 and up 2. And I'm going to say that this graph here is the graph of the square root of x minus 1 plus 5. And what I can do is I can easily check a point on this graph to see if it works. I'm going to check the point up here. It's 2 and 1, 2, 3, 4, 5, 6. So this is the point 2, 6. Now I didn't plug 2 into my equation. And when I say my equation, I'm talking about this here. But what I can do is I can plug it in now and see if my answer checks out. So if I plug a 2 into x, I get 2 minus 1 square rooted, which I know is equal to 1. Add 5 to it, and I get 6. So what do you know? I must have graphed it correctly. Let's do another example. And let's go here. So here's a similar problem. I have an h and a k value. My h in this case I don't really know yet because I don't have it following a subtraction sign. So h is always inside the function, and the function in this case is a x cubed. And I know my h value follows the subtraction sign. So my h is a -4, which means everything moves to the left. My k value follows an addition sign, but this is a subtraction, so it must be a -1. And then my pattern for x cubed would be 2, 1, 0, 1, 2, and 8, 1, 0, whoops, -1, -8. So again, with my h and k, I'm going to translate my origin. Go back 4, 1, 2, 3, 4, and down 1. And I'm going to put a set of axes at the point -4, 1. Then I'm going to take and graph the pattern of y equals x cubed from this new origin. So I'm going to go over 1 and up 1, over 2 and up 8, 2, 4, 6, 8, and back 1 and down 1, and back 2 and down 2, 4, 6, and 8. And I'll graph that guy, and I notice it looks exactly like my x cubed graph, but it's been translated 4 to the left and 1 down. And again, I could pick any point to check. This looks like a pretty easy point here to check, which is the point -3, 0. Plug -3 back into the original problem, and I get -3 plus 1, or plus 4, sorry, is 1, and I cube that, which is still 1, subtract 1, and I get 0, and it checks. So it must be correct. All right. Now what we're going to do is we're going to take and mess with a different variable. All right. We're going to go ahead this time, and we're going to play around with that variable in front of the function. Okay. And we know that variable in this case is our a. So a in this case is equal to 2. If a is equal to 2, then I want to know what happens to this graph. Now, if I were to plug this into my calculator, which I could do, I end up with the following. I end up with point here, and a point here. Now, you could check this in your calculator by graphing the square root of x if you wanted to. But I would just trust me at this point. Now, you'll notice that in this case, if I were to look at the pattern, all right, my pattern is I go over 1 and up 2 and over 2, or actually, I'm sorry, over 4 and up 4. This is the new pattern. My original pattern for root x is 0, 0, 1, 1, 4, 2. You'll notice here, that's for x and y, you'll notice here that all these new y values have doubled. So the effect of a is simply to multiply the y values. So in other words, a is going to be what we call a vertical stretch. I like calling it a y multiplier. The absolute value of a is greater than 1, the graph's going to narrow up. And if it's in between 0 and 1, it's going to get wider. If it ends up being a negative, it's going to reflect those points over the x-axis, which makes sense because positive y's then become negative y's. So let's take a look at another example here. In this case, we no longer have a anymore because we have this value inside the function. A is always a multiplier outside the function. So this is a b value. B is equal to 3. And if I was to graph this function, you would notice the following. Again, I could plug this into my calculator. You'd notice that I would get the following graph. And if I look at the original for x and y's, I know I've got 0, 1, 4, 0, 1, 2. That's my original. And my new pattern, if I were to look at those exact points for x and y once again, I actually get 0, 0, no change, but then I get 3, 1, and 12, 2. And you'll notice in this case, all the y's are the same, but the x's have changed by a multiple of 3. Coincidentally, the b value is 3. So what that tells us then is that b affects the y values. Specifically, b is a horizontal stretch or an x multiplier. All right, and when b is greater than 1 in absolute value, the graph's going to get wider. And when b is in between 0 and 1, the graph's going to narrow up. It's going to squeeze together, if you will. And then if b is negative, we're reflecting over the y-axis, which would make sense since you're multiplying to the x's. X is going from positive to negative. Flip over the y-axis. All right, so now let's look at one more graph, or set of graphs. And this is kind of a tricky take on what's actually a b value. Since it's in the function, it has to be the v value. But in our original, we had f of x minus h over b. So there was a fraction there. And we also noticed that the x value had a coefficient of 1 in front of it. This x value doesn't have a coefficient of 1. I need to have a coefficient of 1 in order for it to be in standard form. So what is another way I can say multiplying by 2 without multiplying? In other words, how can I say multiply by 2 but actually divide? Well, I divide by a half. So now I know my b value equals 1/2. And we just got done saying that b values multiply the original x's. So in my original, for root x, I get 0, 1, 4, and 0, 1, 2 for my x's and y's. But in this case, since my b value is a half, I'm going to take all those x values and multiply by 1/2. So this gives me 0, a half, and 2. Turns out these values here will be my new x's and y's. So what I'm going to do is I'm going to take and go over 0 and up 0. I'm going to go over a half and up 1. And I'm going to go over 2 and up 2. And this will be my new graph. It's kind of a squeezed in version. And again, I'm going to check a point of 2, 2 and make sure I graph this right. Plug in 2 here, get a 4. Square root of 4 is 2. I graphed it right. So let's summarize once again. All right, I have some unknown variables. A, H, and K. And I've got this other variable known as B. All right. And we found that each of them have a different relationship to the problem. The H value slides points left and right. The K value slides points up and down. The A value, which is outside of the function, multiplies Y. And the B value, which is inside the function and in the denominator, multiplies X. Now, on Monday, we're going to put all this stuff together and really create a lot of havoc with the graphs. So we'll hit it then. The homework assignment will be up. We'll see you on Monday.